Franco, can you hear us okay?
Yes, I can hear you fine. Great. And it's great to have you here. And it's a great pleasure and honor to have you here. You have very interesting results. So we're looking forward to your talk.
All right, now I'm wondering which interesting results you were hoping to hear. I'm hoping I picked the right ones. So, okay, so I'm really excited to be here. It's a wonderful opportunity to speak here. And this is actually my first time on this entire continent. And so I was really grateful for the opportunity to come. I'm Oliver Dial. I'm part of IBM Quantum. I'm actually part of our hardware team. So when I'm done here, I'm going to go back home and go back to simulating and designing and testing our quantum hardware devices. But the results that I'm going to be talking about today come from all across of IBM Quantum. We have research in theory and applications in error correction and error mitigation and how to build quantum hardware. And so really it's the entire IBM Quantum team that belongs on the author list for this slide. So the title of this talk is A Mitigated Path to Quantum Advantage. And I'm really thankful for Nathan yesterday for doing such a great job of introducing error mitigation. It's going to let me change the flow of my talk a little bit. Since a lot of us have already heard what error mitigation is about, I'm going to begin by giving a little bit deeper of a dive than I intended on a particular type of error mitigation called probabilistic error correction. It's a technique that has exponential overhead in terms of the target accuracy with which you want to simulate a quantum system, but it still shows advantage over running on a bare quantum system. Using that, we're going to talk a little bit about what sorts of error rates we think we need to see quantum advantage. And then from there, I'll talk a little bit about our quantum hardware, about the fact that it's not there yet, just to kind of spoil the surprise, but about the research that we're doing to hope to bring it there. And then finally, I'm going to use this as an opportunity to talk a little bit about IBM research as a whole. IBM Quantum is an organization inside of that, and the different routes that you have to interact with IBM research and to take advantage of the resources that we make available. Okay, so in high performance computing, in IBM is all about computing. It's all about solving the world's problems using computation. A central question of interest is what's the time to solve your problem? If the time is too long, it probably doesn't matter to you. Now, I'm going to cheat a little bit here on my quantum advantage talk, and the reason is I'm really lazy. I don't want to have to rewrite this talk in 6 months when the world changes. And I'm going to change it from quantum advantage to what's the time to solution for the noise-free output of a quantum circuit. So everything I'm going to do from here on is a little bit independent of exactly what quantum circuit you're interested in running, how deep it is, how wide it is, and just going to talk about techniques for getting the answer. Now, over the last couple of days, we've heard a lot of talks about quantum error correction. This is a wonderful field of research, and this gives us a set of techniques. We're using more resources, and by resources here, I mean more qubits, I mean more time, I mean classical compute on the side of our quantum system. I can give an arbitrarily good answer to this question using polynomial time. And so this is a really amazing technique once you're able to perform it. However, it turns out that there is a barrier that you have to overcome to be able to perform quantum error correction. Here I'm showing a plot that's very cartoon. On the x-axis is quantum circuit complexity. That's how hard is the problem that you want to solve. On the y-axis is simulation cost. And in here in simulation cost, I'm including how many qubits do you need, how good do you need them to be, how long is it going to take, everything that might matter to you if you were a business or a researcher that wanted to solve a problem. The reason why we want quantum computers is for classical computers, this cost is exponential. It becomes a point beyond which we're just never going to be able to pay it. With quantum error correction, this cost is linear, which is wonderful. But before we can even begin to use it, we already have an enormously high simulation cost because we need to put together all those qubits, all of that classical compute, and have these very high fidelity quantum systems. And what this talk is about is trying to find a place. Is there anything I can do to help with the feedback here? To try to find a place, someplace in between that gives us some protection against quantum errors, but without going to the full-blown quantum error correction. We've already heard a lot of mentions of this over the course of this conference. We heard about cat state qubits, which protect you against some errors while making you more vulnerable to others on Monday. We heard about quantum error mitigation a little bit from Nathan yesterday, which sort of buries the lead a little bit again. And of course, we've heard a lot about near-term quantum, which has a very, very low simulation cost. It doesn't really matter how good your qubits are at some level, but there's a very open question. This line only goes so far to the right now, left now, that there's a point where the qubits just aren't good enough anymore. And does that blue line intercept the red line? I don't think anyone really knows at this point. Okay, so what's the third method I'm going to talk about today? It's called probabilistic error correction. As I already said, I'm going to put all the negatives out front. It has an exponential cost. Okay, this will not let you go arbitrarily far like quantum error correction will, but that exponential cost is weakly exponential. I'll explain what I mean in the future. It only can give you expectation values. So if you care about the individual bit streams that come out of your quantum algorithm, like you would if you're doing Google supremacy experiment, if you're doing a quantum volume experiment, if you're doing Shor's algorithm, this approach will not help you. But it will help you if you're interested in expectation values, which is what you care about for a lot of problems in condensed matter physics, in quantum chemistry, in machine learning and optimization. And so for many applications and for many users, if you can solve the problem that you care about, there is no practical difference between probabilistic error correction and quantum error correction. They just want to know, can you get the answer or can you not? Okay, so to explain probabilistic error correction, I'm going to start out with a very simplified model. This is a very toy model. I'm going to consider only one qubit, and it just has a simple amplitude damping channel, T1 only. And so we can think of this channel as just probabilistically applying a bit flip to the qubit. So with a probability 1 minus p, at every time step, the qubit goes through unimpacted. With a probability p, we flip the state of the qubit. And by the way, if you want more detail on this, there is a wonderful and much longer YouTube video quoted up there. Now, with probabilistic error correction, what we want to do is do something to our qubit that's going to undo that T1 error. Now, that's impossible. The reason is the inverse map of this actually needs, right, that this bit flip channel takes the state space available to the qubit and shrinks it. To undo it, we need to make it bigger again. Nonetheless, let's just close our eyes for a moment and carry on, and let's make a guess. What we're going to do to our qubit to try to undo this bit flip error is with a different probability, 1 minus q, I'm going to leave the qubit alone. And with a probability q, I'm going to flip it again. Now, that may seem like a really weird ansatz, but let me give you an analogy that maybe makes it easier to understand why. Let's imagine I have a biased random walk. And so I have a little guy here with a probability 1/2 plus p, he walks to the right. It's really hard to mirror this in the room. With a probability 1/2 minus p, he walks to the left. And so if I consider this random walk as a function of time, the position is biased. He wanders to the right, to the right, to the right. But if I wanted to, I could add a second process where from time to time, I'm going to give a little puff of wind and blow him back to the left. And if I match the probability of my wind blowing him to the left to the probability of him going to the right, then my process becomes unbiased. He always stays at the origin. The penalty I pay for this is the influence of these two random processes is going to make the variance bigger and bigger. And so if my job at the beginning of the day was to estimate where he was, I'm going to have to measure his position more and more times the larger these errors are. We can go through this same sort of analysis for our qubit. And we see in the first case, can you guys see my mouse, I hope? With a probability 1 minus p times 1 minus q, the qubit didn't decay due to T1. I didn't do anything to it. There was no error. With a probability of q times p, the qubit decayed and I flipped it. And again, there's no error. But with a probability of 1 minus q times p, the qubit decayed, but I didn't flip it. And the probability of q times 1 minus p, I flipped it, but the qubit didn't decay. And so our job in this probabilistic error correction is to try to take these two errors and set them so that the sum of those two probabilities is 0, to remove those errors. And if you do a little bit of algebra, you can convince yourself that this is possible. And the answer is that you need the probability to be minus p divided by 1 minus 2p. For small errors, you basically need the probability to be minus the probability of the qubit flipping. Now, this is where all the experimentalists in the room usually start getting a little bit mad at me because they say, wait, so you're saying if my qubit had a 5% chance of decaying, I should apply a pi pulse with a minus 5% probability. How do I do that? And the answer is, well, yeah, of course you can't. We already knew that we were not going to be able to undo this map, that it's a non-physical process. However, we can play a really nice trick. And the trick that we play is we add the word quasi to that probability. And what's kind of neat about quasi-probabilities is they're allowed to be negative, and we're allowed to talk about expectation values of them. So now, instead of actually trying to run that experiment with a negative probability, what I'm going to do is run it with a positive probability and keep track of the answers. And then when I want my expectation value, I'm going to do a weighted average of these answers. And I'm going to assign to that particular experiment a negative probability. And so I'm going to get the same answer mathematically that I would have had I been able to run that experiment a negative percentage of the time. So this is where the limitation on probabilistic error correction comes from, that it only works for expectation values, not for any kind of sampling problem, because I need to move to expectation values to be able to play this weighted average trick to be able to use negative probabilities. Now, I do pay a price for this, the same as we did with the random walk where the variance increased. In this case, when I do that weighted average, I need to divide by the sum of all the weights. And because of those negative probabilities, the sum of all the weights is now less than 1. And so I'm actually going to do this weighted average, and I'm going to multiply the number by a number bigger than 1. And so I'm going to blow up my noise a little bit. This number gamma at the top right corner, sorry, I have to keep on turning around to figure out right from left here. This number gamma at the top right corner is in fact that amount by which you need to blow up the probabilities. And you can see that the larger the errors that you're trying to correct for, the larger gamma becomes. Okay, so how does this work in practice? Remember, the goal here is we're going to start with some circuit that we care about, and we're going to try to average over many more circuit instances with these additional gates, just like that X gate I inserted. And we're going to get mitigated expectation values where the expected value of these is perfect, even though my quantum computer isn't. The first step is we write down the circuit that we care about. And as Steve Flamia mentioned yesterday, we polytwirl each one of the stages in our circuit. As an experimentalist, that's really important to me because that takes a lot of non-Markovian problems, drifts in my experiment, drifts in the environment, and turns them into simple types of noise that I know how to do with. The second step is that I need to learn the noise. I'm not going to go into a lot of detail here because Steve spoke about it extensively yesterday. But in order to correct for the noise, I need to be able to generate a detailed and very exact model of the noise in the quantum device. This is actually one of the trickier things in this technique because it means that your quantum device needs to be stable enough that from the time that you learned the noise, the time that you execute the circuit that you care about, this model hasn't drifted. So this is a really challenging and actually a little bit hard to quantitatively talk about limitation. Then we error mitigate. And so to do that, I insert all these probabilistic gates that are designed to exactly cancel the noise model. The computation, if you have multiple sources of error in your circuit, as opposed to the single source of error I had in my T1 experiment, is a little bit more complicated, but it's just a little bit of matrix algebra. And then finally, I calculate my expectation values. So here's a very simple example of this in practice on a real device. Here we're running a really dumb circuit. We prepare all the qubits in the excited state. We perform 2 layers of C0 gates to make an identity. And so if our quantum computer was perfect, the qubits would always still be in the excited state at the end. And then we look at correlators. We look at, was 1 qubit in the excited state? And the answer is, well, usually, it doesn't really depend whether we mitigate it or not. But then we look at 2-body correlators, where pairs of qubits in the excited state, where 3 qubits at a time in the excited state. As we add more and more qubits, the probabilities of failures multiply together, or success multiply together, the probability of failure gets higher and higher. Without PEC, you can see by the time we go to the weight 50 correlator, we have basically no probability of finding the one that we expected. But with probabilistic error correction, we recover a nice high probability there. So this is really kind of a beautiful result. Okay, I said the sampling overhead was exponential. We can extend that gamma that I used in the single qubit case to a quantity that we call gamma bar. And you can think of that as the sampling overhead. It's approximately 1 plus the average error rate on your different qubits times a prefactor that depends a little bit on the details of the circuit that you're running. And the number of additional times that you need to run this circuit to make your answer more accurate is exponential in that gamma bar times the number of qubits in your circuit times the depth of the circuit. And so for this to be, as I said earlier, a weak exponential, you really need your error rates to be very small. So some of you are probably asking, well, should I use this? Well, if what you care about is accurately estimating the sum observable of a quantum circuit, I would say, well, yeah. I mean, let's take an example of 100 qubits at depth 100. So that's this blue line. If I have an error rate of around 10 to the minus 3, which is around the day where we are today, I'm trying to run 10 to the 4 gates, I have absolutely no chance of succeeding at solving this problem. This is way outside of the realm of what my quantum computer can do. On the other hand, if I'm willing to apply probabilistic error correction for about a day on the kinds of speeds that we have on our computers today, I begin to be able to get an accurate expectation value out of this. So that 1 day of runtime brought this problem from something that I could solve today to something that would really need an error rate of 10 to the minus 4 in. This story scales very nicely with error rate. If my error rate had been 10 to the minus 4 with about a day of runtime, I could have made my error rate look more like it was 10 to the minus 5. No matter how good your computer is, you will always be able to do a little bit better with this technique. On the other hand, you're never going to do infinitely better. The other thing that we really love about this technique is you'll notice I didn't do anything outside of the circuit model to make it work. There's no stretched gates, there's no zero noise extrapolation type of approaches. And that means that this is a technique that we might be able to layer on top of error correction algorithms. And somebody mentioned this yesterday, but I don't remember who, I'm sorry. Because with most error correction algorithms, there are some gates that are very easy, and those are called the transverse gates. There's some gates that are very hard to perform and actually occupy a huge fraction of the overhead in running these algorithms. And so the idea would be to run the easy gates with your error correcting code and use your hard gates to use probabilistic error correction. So this is a technique that we think not only has immediate applicability in near-term computing, but we think will bring the era of quantum error correction closer to us. So the key question here now is, okay, we have our exponential red line for the classical computer. We now have a slightly shallower exponential for quantum error mitigation. Where is that crossing point? How good do we have to be before this technique will bring our quantum computers beyond a classical computer? Now, the answer to that question depends on the problem, right? Obviously, I could choose a problem that was easy for a classical computer anyway, and this would be never. So let's assume we've at least chosen a problem that's exponentially hard for a classical computer. I'm going to choose a specific problem, which is an Ising spin problem. It's probably one nobody cares about in a very practical sense, but it has the advantage of being very well studied. And for this problem, we can estimate on the Orion supercomputer, it's a particular one, nobody really cares, how good my qubits would have to be to beat that supercomputer. If I do a naive full state vector simulation, you can see I need that gamma bar number to be less than about 1.01. And I need more than 56 qubits. And that 56 qubits number is in there because I need to be able to rule out certain tricks people could play by trading off memory against time in their computation. But that's sort of cheating a little bit because that's not the best way to do it. If I use the best classical method, which is a tensor network method, I need a gamma bar of about 1.003 and 100 qubits to be able to hit that point where the red line and the white line just cross each other. And here I'm looking only at runtime, not the actual cost of the machines. So how far away is that crossing point? To talk about that, let me take a break for a moment and talk a little bit about what we do. This is the picture of one of our labs in Yorktown Heights. Each one of those pillars that you see has behind it a dilution refrigerator. Each one of those has a quantum computer inside of it. One thing that we do and a few other people do now that's a little bit unique is when we build these quantum computers, the old way of doing things, you would make it, you would run some quantum algorithm on it, you would write a paper, maybe you would write a couple of papers, and you'd go back and make a new one. And so if you wanted to do quantum information science, the barrier to entry was first you had to build the quantum computer you're going to do it on. We take these quantum devices and we make them available to the world. And we don't do that in particular because we're hugely generous. We do that because by working with other researchers in the world, by working with customers, by working with clients, we learn more about quantum information science ourselves. This is how we learn what we need to know to make the next generation of devices better. If you look really carefully at this picture, you'll notice one of those fridges is unwired and another one is open. We are constantly changing out these devices to put in the best and the greatest that we have, and then we let other people tell us if we succeeded. It's kind of a fun way to work. I'll get to that in a moment. Great question, though. So at the moment that I took this screenshot, we had 23 quantum devices online. Some of these you can have access to free. If you go to quantumcomputing.ibm.com, you can get started with Qiskitty. You could just use them. Some of them are available to our academic partners. Some of them are specific to specific other corporations. We have other venues to get access to them. We have an educators program for education. We have a researchers program. There are many, many ways to get access to these devices. And these different columns of numbers here are different metrics that we use to evaluate these devices. And I'd just like to point out, they're all different. And I'll get to the reason for that in a moment. One really fun thing that I'm proud of, very proud of, is there are almost 1,500 papers written on these devices by people outside of IBM. You don't have to have the capability to build a quantum computer to do world-class research in quantum information science. That this number just keeps going up and up. Okay, so I've already told you, none of these devices is good enough for me to get that red line to cross the white line. And in a very general sense, we have three problems. Our performance isn't good enough. Our performance isn't good enough because we don't have enough qubits. Our performance isn't good enough because those individual qubits have high error rates. And so they don't have the high enough fidelity to get there. And our performance isn't good enough because our processors are slow. If we could make them 10 times faster, I could run 10 times more circuits in a day and I could bring this PC even farther. We work on these problems in parallel. We do that because it would be possible to wake up any one day and say, well, today quality is our biggest problem, so let's work on making T1 longer. But there are a couple of problems with that. One is that a lot of this research is very long-term. We don't really know exactly how we're going to make progress. And so if we serialize this, we're never going to get there. The other issue was trying to serialize work on this. So we work on one, then the other, and the other is we would miss out on all the synergies. We'd miss out on the fact that sometimes changes that we make to try to improve scale would also improve quality at the same time. And we work on all of these problems iteratively. People sometimes talk about the gap between the quantum hardware that we need to run the algorithms that we care about and the quantum hardware that we need to run today. And I would add to that the gap between the quantum error correction that we have today and the quantum error correction we wish we had. So if we worked on these by shooting for the stars and saying, we're going to make the system that we need to run the quantum algorithms that we really care about, we would miss out on all the incremental improvements that are happening every day in all these fields. And so we want to constantly innovate, constantly change our devices and learn all the time by actually doing things. To answer your question, our qubits are based off of superconducting transmon qubits, which we've heard about throughout the week from time to time. And so I'm not going to go into too much detail about them other than to mention briefly the one thing that makes ours a little bit different from most people's is we use what are called fixed frequency transmon qubits. That means there's only a single Josephson junction. The day that we build them, the frequency of this qubit is chosen, and aside for some annealing tricks, it never gets changed again. That has some advantages in coherence. That has some disadvantages, actually a lot of disadvantages. I'll mention one of them in a few minutes. So I'm going to take a moment and talk to you about how we're working on scale, how we're talking at speed, how we're working on quality. So for scale, one of the big problems, and Dr. Sai mentioned this on Monday, is each one of these qubits is controlled and measured by microwave signals. And so if we have a lattice of qubits, we need a way to get those signals in, and we need to get those signals out. In our so-called generation 1 packaging, which is where a lot of people live, we have one layer of metal on top of a chip. We have wire bonds to bring signals into the edge, and we have to bring the signals in from the edge to each qubit. And this works really, really nicely if your qubits are in a ring, but it breaks down the instant that you want to put a qubit right here in the middle. So that brought us to what we call our generation 2 packaging. And what we did here was we added a second chip to the stack, and we added superconducting bump bonds between our qubit chip and the interposer wafer. And the neat thing now is I can put my qubits on one of these wafers with all the bus couplers that connect them, but then I can bring the signals in on the bottom wafer. That lets me have signals cross each other because I have these two clean interfaces. I can route signals right into the center of the chip. But it has some disadvantages as well. These metal layers aren't particularly well isolated from each other. When we get down to the details of the processors, our Falcon processors are made in this generation 2 packaging, our 27 and 65 qubit devices. The most recent generation that we just released earlier this year is what we call our generation 3 packaging. And here we've added 3 key new features. One is in the qubit chip, we now have superconducting through substrate vias. And it's a little bit technical, but these let us create Faraday cages around the qubits that keep them from broadcasting radio waves through the chips. We added superconducting through substrate vias to the interposer. That serves the same purpose, but it also lets us reach a buried layer of wiring that's actually inside of the wafer that's also superconducting, that gets us ways to get signals deep into the center of a chip without any crosstalk to anything else. And this is the technology that we're using in our newer 127 qubit processors. And if you remember that table before, you'll remember that one of our requirements for getting that red wine and white wine to cross was getting above 100 qubits. So that's one of those lines ticked off. Just because I think it's really fun to look at, here's a cross-sectional view of some of our superconducting multi-level wiring. Here's a little strip line. You can see vias off to the side that actually make a Faraday cage around it. This is sort of a fun picture because you show this to physicists in the field and they're like, wow, how did you build this? And you show this to CMOS engineers and they're like, that's back end of line wiring. Why are you bragging? That this is for serious foundries, really nothing at all to do, but getting to work in a cryogenic environment with the superconducting devices really was a bit of a game. And just to show you it really works, here's driving a current through 13,000 vias through one of these multi-level wiring layers in series, showing that in fact, we can do an enormous number of these guys entirely superconducting. So this was the basis of our Eagle processor. To put it a little bit in perspective, in 2011, this was a 3-qubit system that's analogous to the first ones that we put online. Our Eagle system on the right with all those extra layers. Now, my job's kind of funny. When I'm done with one of these, I don't try to run circuits on it. I don't try to write a paper. Instead, what I do is I poke at it and try to break it and find the worst features of it at all. And so just to give you a little bit of a feeling of that, a particularly nasty problem for probabilistic error correction is crosstalk. And here I'm going to talk about microwave crosstalk, which is where I'm driving a signal. I'm trying to get this qubit right here. But because of some defect on the chip and the wiring and the design, just a little bit of microwave signal leaks over to some other qubit over here. And the reason why this is a particularly bad problem for probabilistic error correction is that this type of problem doesn't have to be local. Depending on how the wiring on my chip is routed, this crosstalk could actually go to a very distant qubit on some other corner of the chip. And that totally breaks the way that we estimate our noise models. So this is a really bad thing that we would like to avoid. Of course, our qubits are also coupled on the chip, and that looks a little bit like crosstalk, and we have to be able to disentangle these effects. So what we do is kind of a neat trick. We use something called Hamiltonian tomography. We drive the what we call the victim qubit, the qubit that we didn't want to, through the port that we wanted to use, and we look at how it evolves, and that lets us estimate the microwave field that it's receiving. Then we flip the state of the qubit that we did intend to drive up here, and then we do the same experiment. And so the change in the evolution of that victim qubit tells us how much of that evolution came from microwave crosstalk and how much of it came from direct coupling. And so it lets us distinguish between those two problems. Now, if we do this and we compare that generation 2 packaging, just those 2 bump bonded layers like we use on our 27 qubit SAM processors, to this generation 3 packaging, these Eagle processors, you can see that it's uniformly better. And just to explain this plot very quickly, there's 16,000 pairs of qubits in the Eagle processor. I can't show you a diagram of all of them. And so this is a very quick way of comparing large distributions. Here I've taken all of the crosstalk numbers written as percents. So 0.01 means that 1% of the microwave amplitude that I shot at the control qubit went over to the victim qubit. I've taken them, I've sorted them, and I've plotted them just by number on the x-axis, value on the y-axis. So if you wanted to see the median crosstalk, you would look at the value right here. It's pretty close to 0 for both of them. If I wanted to know how many of the qubits had a crosstalk above 1%, say, I would look at how many qubits are above this blue line right here. You can see that the crosstalk on the Eagle processor is uniformly better than it was with our generation 2 packaging. That's really nice for us to see because that's not something that you necessarily naively expect. Usually when we make our chips bigger, the crosstalk gets worse because they're getting larger and microwave wavelengths and everything turns into antennas. I'm going to skip a few slides here. On speed, I'm going to call this out. Remember, speed lets us run more circuit synthesis, makes probabilistic error correction more work better. I'm just going to bring this out to point out there is a lot more to our processors than just the chip in the fridge. There's the software that takes the circuit from you through the cloud into our lab, programs the microwave generators, turns on the sources, measures the results, and sends them back to you. That's our QA6-Kit stack. There's the ability to measure the qubits themselves, which has to do with this device design. And then there's the control hardware itself that generates those microwave pulses that we need to be able to quickly reconfigure for your job, and then for your job, and then maybe if I'm lucky for my job. And so making our processors faster isn't just a matter of making the hardware better, it's about making the software more efficient. It's about making this control hardware more quickly reconfigurable. There are many, many aspects to it. One thing that I do want to point out that's cool because it's a little bit new and not a lot of people know about it is this QA6-Kit runtime. For a lot of these algorithms, there's mixed quantum and classical computation. In the case of the probabilistic error correction, it's pretty simple. It's this weighted averaging. In the cases of QA/OA, for example, it's more complicated. You're doing a classical optimization with a quantum center loop. What Qiskit runtime actually lets you do is take the classical part of your algorithm and run it on our computer, not yours. And the great thing about that is that means your algorithm is running right next to the control hardware, and you can get enormous speed ups out of this. To put this in perspective, today we measure this in a really weird unit called clop. I usually just think of horse trotting. Our speed is about 1,000 clops. We hope to be at about 10,000 clops by the end of the year. In the context of that plot I showed you, instead of 1 day of runtime to get that factor of 10 advantage, that means 2 hours of runtime to get that factor of 10 advantage. And that sounds like a lot more fun to me. Finally, quality, and here's where you're really going to begin to see the parallelism in this development process. On the left, you see a T1 trace for one of our coherence test devices. We don't really do coherence research on these large devices. They're too hard to measure and too expensive. We use much smaller ones. This was published on a peer-reviewed service called Twitter. There were some comments on it. And this was actually the first T1 we saw in our lab that was above about a millisecond. At the time that this was measured, we were making our Falcon R5 processors. This is another one of those quantile plots. And here I'll point out a second feature of these plots, which is that the x-axis is distorted as the error function of the number. So on these plots, if I have Gaussian distributed data, it makes a nice straight line. And so you can see for Falcon R5, T1 was more or less Gaussian distributed, and it had a median of about 120 microseconds. About 9 months later, working in parallel to building Eagle, we were able to incorporate some of those changes into Falcon, and that created Falcon R8. You can say we were able to bump up the coherence time from a median of about 120 microseconds to 250 microseconds. We were really happy. About 3 months later, our first Eagle processor came out, but it was made the same way as Falcon R5 because we did these things in parallel, and so our coherence times went back down to 100 microseconds. And we heard over and over again, oh, IBM made its processor bigger and you can't make big, highly coherent processors. And this is why we can't scale. But the real answer is you were seeing kind of a little bit of motion lag from the fact that all these efforts were happening in parallel. And in fact, about 3 months later, our first Eagle R3 processor, don't ask about Eagle R2, not everything we did works, came out with a median T1 of about 300 microseconds. And so if you look out into the future for the test devices we're making today, you can see we now have new processes where we're routinely seeing 1 and 2 and even 3 millisecond coherence times, but we don't yet know how to integrate those back into our large devices. Finally, in addition to coherence, we work on gate fidelity. We have a new fundamental basis for how we're doing our gates based off of a tunable coupler architecture with fixed frequency transmons. The details don't really matter for this talk. But what is important is that instead of the sort of 0.75% median error per gate that we were seeing previously, with these new devices, we're seeing closer to 0.2% error per gate median across the device. And so if you go back to that plot where we're looking at fidelities, that means we're getting now down into the region where it becomes reasonable to talk about running a circuit with about 10 to the 4 gates in it, which makes us pretty excited. Okay, so now we're ready to go back and actually understand a little bit how close are we to that red and white line. Brooklyn here, all of our devices have names of cities. That doesn't mean it's actually in Brooklyn, is one of those Falcon R5 processors, the low coherence 27 qubit. Ithaca, Falcon R8, high coherence 27 qubit. Prague is that new gate architecture that I just mentioned. We only have that available in a 33 qubit architecture. So none of these meet that 100 qubit threshold that we need to pass. But if we look at the quality metric, you can see that we're really edging in on that 1.003 that we think we need to meet to begin to hit that intersection point in the next couple of years. And I think we're going to get there. And the reason is we're not in this in the short term, we're in this in the long term. This is our development roadmap. We release this every year to give people a feeling for where we expect we're going to go. You can see Eagle here, 127 qubits with a check mark next to it. Osprey is the device we intend to deliver this year, 433 qubits. No, we don't need them yet, but as I said, we work on these problems in parallel. And actually, the main thing that Osprey is testing is something that got mentioned on Monday of this conference, is the ability to use flex wiring to deliver signals to our chips instead of coaxial cables. And so this is a big step in scalability when we demonstrate this working. And the one that actually has me the most excited sometime early in 2023 is this Heron processor. That's the 127 qubit version of that high gate fidelity device. Now, it may not work, but we expect it to. And that's going to bring us very, very close to the point where those red and white lines cross. Now, let me just take one last few minutes, if you'll forgive me, and talk a little bit about IBM research. We say we're the organic growth engine of IBM. What does that mean? Well, IBM is a company about computing. That means to stay in the forefront, we need to be in the forefront of research about new modes of computation. It's really easy to see why IBM is very interested in quantum computing. We have about 3,000 researchers scattered around the world in hundreds of disciplines and worldwide collaboration. You can see on the list at the bottom different areas that we're doing research in, but the kind of things that I really wanted to show here is top middle, that's Yorktown Heights, that's the lab that I work in. That's the focal point for our research in superconducting qubits. Bottom center is Zurich Research Lab. That's the focal point for our research in semiconductor spin qubits. If you look across the world, we have labs, and I want to say the number is 12 countries, but this changes from time to time. And the thing I really wanted to point out in this audience is that we have our South African lab that's split between Nairobi and Johannesburg. And I don't know why that slide's there. It was meant to be earlier. And just to zoom in a little bit on that, I wanted to point out a couple of things. First of all, we have some quantum applications research happening in our Africa lab that's very exciting. That's actually mixed between the Africa lab and the Zurich lab that I mentioned before. But also, Ismail and Gemma are both virtually attending this conference. And so if you have any questions about the South Africa lab, about how any of this works, you should be able to get them on the Zoom chat. I really hope they're there right now and not making a liar of me. And the final thing I wanted to point out is this collaboration with Wits University. Now, to go back to that slide I just flashed away from, this is a list of what we call our IBM Quantum Network members. These are institutions, companies, academic consortia, national labs that have enhanced access to our quantum systems, either in terms of access to larger systems, higher quality systems, or just prioritized access. I think we already heard a complaint about how long the queues are on some of our free systems. And if you look back down here, right at about number 170, they're alphabetical here, you will see Wits University. In fact, Wits University was our first African IBM quantum network partner. We've run summer schools there. We've run what are called quantum challenges there, which are really fun ways to learn about quantum computing. But also, almost as importantly, they're the gateway for, I don't actually know how to pronounce this, ARUA, it's an acronym. And through Wits University, this IBM Quantum Network Partnership is available to academic institutions across Africa. So this African Research Universities Alliance includes 16 universities in 10 countries. And yes, in fact, that includes the very university that we're standing at right now. So this is a path for anyone here, or many people here anyway, to get enhanced access to IBM quantum systems. This is aside from the researchers programs, the educators programs, the free programs, and if you're really interested, the pay-as-you-go plans that we have available. So if you only take one thing out of this entire talk, I would say it should be, you can absolutely do world-class research in quantum information science, even experimental world-class research, without having your own quantum computer. They're available to use, and they're not just available to use, but we want you to use them, because by you using them, you help us make them better. You help us learn about better quantum algorithms. And yes, we're a corporation. You help us create future markets for our technology. So this is just a fun little animation. Each little sparkle is one execution on one of our quantum computers around the world. If you watch really, really carefully, you will see a dot in Antarctica. That's a fun thing. The ISS does not appear on this, even though it's been used from there. And you know, in the same way that the growth in the use of our systems has just been nonstop, we really don't see any indication that this technology is hitting a barrier. The coherence times continue to get longer, the gate fidelities continue to get better, the control hardware continues to get more scaled and cheaper. And so I think we're in for a very exciting time. Thank you very much.
Thank you very much for a great, great talk. Fantastic. Would you mind showing the previous slide when there is the map of Africa?
Yep.
And exactly there. So therefore, the blue dots are, these are not there are no IBM queues in every dot. It's only there is one in South Africa. The other ones are, would you mind repeating what they are?
So these two dots, Nairobi and Johannesburg, are the dual sites for our IBM Africa lab. IBM Africa Lab and IBM in general has this collaboration with Wits University. They are an IBM Quantum partner, but they're also the gateway for that partnership to the African Research Universities Alliance. And my understanding, although I have not personally tried this, and you should really talk to Gemma or Ismail for details, is that through this alliance, all of those universities are able to gain access to the resources through that partnership. And I really hope I'm not lying. Gemma swore it was so.
And Rwanda is part of the partnership?
Yes.
Okay, good. Good, great. Excellent. This is, I see.
And please do reach out to Gemma. That she would be delighted to hear from anyone here. And she's very helpful.
Okay, great. Excellent. So we have questions in the chat. Let me just
Actually, Omo has much.
Oh, okay. There's Gemma Dawson, right? Gemma Dawson, right? In the chat. No, there's somebody in the chat.
Well, in the chat, there is a question by Xing Yao Wu. Thank you, Oliver, for giving the wonderful talk. My question is, when you apply additional gates to mitigate the error, how do you make sure these additional gates are error-free?
I'm ashamed to say I hadn't thought of that particular question. My experimentalist answer is quick and off the cuff that those additional gates are single qubit gates, which in practice are much higher fidelity than the remainder of gates in our system. I do not know the answer to that. Does anyone in the room happen to have a better answer than I don't know?
But this could be a good homework problem for the students in the audience. Now, there is another question by Mahoro Esther. Nice presentation. For sure, you're doing an amazing job. My question is, does it work on any number of qubits?
Yes, it does work on any number of qubits. And in fact, one of the nice things about that simplified error model that I was showing is that the number of qubits and the depth trade off in the same way, that you can just the number of qubits times the depth. But that also points out the hazard in going to more qubits, that the cost is exponential in the number of qubits as well. So yes, it goes to any number of qubits, but with the but that you hit an exponential wall at some point.
There is a question posted on the chat right now by Unati Scosa. Can you say a little bit more about dynamic circuits, how they will fit into the already existing framework, and what kinds of benefits will they offer to end users? When are dynamic circuits expected to be supported by hardware?
So this is an interesting question. I wish Blake was here today. So for the audience, dynamic circuits is the word that we use, at least at IBM, for the ability to measure a qubit and then at some point in the future to use that measurement to influence the future circuit. So measure qubit 1 and then a little bit later on qubit 2, either do or do not do a NOT gate, for example. And there have been examples of dynamic circuits in the literature for a very long time in many simplified cases. It actually turns out it's easier to make the hardware to support dynamic circuits than it is to make the software that makes it easy for the users to use, because being able to express within the context of a quantum circuit classical control flow is quite complicated. We've had the hardware for a couple of years. The QASM-3 standard, which is an open standard for sort of an assembly-like language for quantum circuits, supports dynamic circuits. And if you're willing to write your circuit in QASM-3, it is currently supported by our hardware. There's also beta level support for this through Qiskit available right now. And actually, if I'm really smart, I can't figure out how to see the chat and not close this at the same time. If you'd send me an email, I'd be happy to point you at the documentation for the beta implementation.
Oh, great, great. Thank you very much. No, I had a similar, we have been trying to implement one-way quantum computing using the IBM Q devices with collaborators, and we needed more dynamic control, and we didn't have it last year when we published the paper, but I'm told by Paul Nation, I think it's coming up this year or perhaps next year, so it will be soon available. That would be great.
Yeah, I mean, if you want to do it in CASM 3, you can do it today.
Oh, great, great, great. Okay, so I'll let my collaborators look into this. Okay, good. Any questions in the audience there?
Okay. Yep. Yeah, so the question was, I showed the improvement in the 2-qubit gate. Is all of that hardware? Is that also improvements in the gate calibration protocol, et cetera, et cetera? All of the other devices we make use cross resonance as a gate. And so that's basically driving one qubit another qubit's frequency to get an gate. This is now a tunable coupler approach and only a tunable coupler approach. And so it's entirely new calibration protocols, entirely new everything. So it's a little bit hard to disentangle those two. But one of the big things that it does for us is if you look at our fidelities, but most noticeably the older devices, there's a long tail of very bad gates. Right. If you look here, at some point, the line goes almost straight up. Those correspond to frequency collisions. Cross resonance doesn't work if you have two adjacent qubits at too close to the same frequency. These new tunable coupler gates greatly open up that collision space, and that's one of the big reasons for this improvement. Any other? Yep.
Is the Condor device available now?
Let me answer Omo's question first. What materials do we use in our device?
Okay.
I'm sorry, that's not a question we answer. Your question was, Franco?
Oh, is the Condor processor available now?
Condor is slated for 2024. We're designing it today. Osprey, we're testing in the lab, and we'll hopefully be available to end users early in 2023. And Heron is in fabrication right now. So Eagle is available.
So the state of the art now will be Eagle processor, no?
Yeah, so the R10 is, sorry, I apologize for our naming convention. One of my bosses, I won't say which one, really likes birds. So R10 is a 33 qubit device. It's very exploratory. The intent right now is probably not to expose it to the world because it's a little rough around the edges right now. We just don't think it would be fun for somebody that wasn't really dedicated to keeping it working. So the first device that we anticipate making available will be Heron, that technology. And that's just to give a little bit of time for our software and our control stack to catch up.
Great, great. There's a question on the chat by Dev. He says the IBM quantum processors are free of cost initially, but now these processors are paid. And then he writes, I request to you to make this again for free for non-business purposes, especially for those researchers who have no financial support.
Okay, so there are a mixture of what we call free and premium processors. I honestly don't know which ones are free and which ones are premium at this particular point in time. And it is a true statement that the free ones sometimes have rather long waiting lists. Sometimes they don't. It just depends on when you're looking. If you are doing just pure research, there is the IBM Quantum Researchers Program. If you Google it, you'll find it, that can provide free access to some of the premium processors if it will help in your research. I mean, if you're using our processors, we want your research to look good. But at the same time, you know, part of the way that we do fund our effort and continue to progress is by other companies paying us for access to the high-end processors. And that may sound like a very strange business model to you, but at the same time, people routinely pay money for research equipment And this is another of that. And it's just part of what enables us to do the rest of what we do. So, but I promise you, there are still free processors.
No, this has been great for many students around the world to be able to tinker from a distance. So I heard like very, very positive comments about students being able to access the free devices, and those ones have been great, great. So any more questions in the audience?
Yeah, we have.
Yeah, I guess just one more comment about I think the first question was very interesting about how you know that the additional gates don't also have errors. Wouldn't those then be a second order effect because you're applying them with probability P and they have P error? So it's more of a P squared. Could that be why? Okay.
What I just said for the rest of the audience is I think Tron's answer is better than mine. But I'm certainly going to go back. Yeah. I am definitely going to go back and talk to my theory colleagues and see what they say. So if anyone's really curious, again, send me an email and I'll let you know. I'm going to stick to my earlier statement.
Some of the earlier devices seem to have many connections because perhaps the logic was the more connections you have, the better you control it. But over time, sometimes some of the newer devices seem to be more minimalist. If you look at Eagle, there are quite a few connections here and there. Falcon seems to be a bit less. And so, of course, if it is less connection, then you get less source of decoherence because then you're interacting with the environment less. So there seems to be a trade-off between being highly connected to everybody and then decohere, or less connected and have longer coherence time, but then you have less control. Do you have any comments on this? Or?
Yeah, sorry. I apologize for turning the slides off. I was hoping I could quickly find a quick explanation of this. The main motivation for that comes from the frequency collision problem that I mentioned before. That our earlier devices, each qubit had between 4 and 9 neighbors, depending on exactly which device you were looking at. And so that meant that you had to worry about any of that set of qubits having the exact same frequency. By going to this arrangement that we call heavy hex, so these alternating patterns. So by going to this alternating pattern of 3 connections and 2 connections, you go to a graph that can be colored with only 2 colors, 3 colors, sorry. But there's also a particular advantage for cross resonance that qubit that only has 2 connections, it can be a target for both directions, which really relieves the frequency crowding problems. I could draw a drawing that would make that clear perhaps. But at a more fundamental level, what we're doing here is we're reducing the connectivity as a penalty, but we're increasing our gate fidelities as the advantage. And so for any given algorithm you have, you're going to map it to this actual quantum device. The reduced connectivity is going to force you to use more swaps in your algorithm, but the increased gate fidelity is going to make those swaps as well as the gates that you actually had in your algorithm work better. So whether or not this trade-off is advantageous really depends on the details of exactly what you're running. The motivation for us to do it is that for most cases with a smart swap mapper, which we do have, this turns out to be a big win. And the other motivation is we are able to demonstrate that you can run an error correcting code very similar to the surface code on this heavy hex topology. And so we were confident that we were doing this without mortgaging our future in the distant future. I hope that answer is helpful. Oh, the other thing, the drawing that I can't quite do because I don't have a chalkboard here. If you do a quick search for the heavy hex topology, I think you'll find an IBM research blog entry on this question that explains it in a lot of detail. And I hope you can hear me.
Yeah, I think I've seen that blog some time ago, and I'm glad you raised this issue. Okay, good. No, excellent. Okay, any more questions from the audience there or Omololu?
Looks like no questions here. I think everyone's hungry for lunch.
Well, I would like to thank you for the great talk, great overview, and there has been a very nice presentation of the great things you're doing there. So, and thanks for going there. I hope you enjoy your stay there.
It's been wonderful. Everyone's been very friendly.